This is our third podcast of our gases unit. So far we've looked at combined gas law that shows the relationship between pressure, volume, and temperature. And when you change one or maybe all of those variables, what's going to happen? Then we looked at Dalton's law, which just said you combine all the gases that you're going to, if you just add them all up, it's going to equal to the total. Then we had Dalton's law, or excuse me, ideal gas law, which is more kind of looking at one gas under one set of conditions that you could either answer pressure, volume, moles, or temperature. So now we're on page 11 and we're talking about, really it kind of falls more with the combined gas law. We're going to talk about those moles again. And so really just remember moles. When you talk about moles of a gas, okay, it's just really how much is there? How much gas is there? We just, in chemistry, we talk about it in moles. So if I have 1 mole compared to 2 moles, if you have 2 moles of gas, you have more stuff. You have more moles of gas. So then this math kind of makes more sense. So if I have more stuff, it's going to have a higher pressure and it should occupy a greater volume, because if you have more moles, there's more stuff, it's going to need more space. So Avogadro's principle started looking at the relationship and saying, if I have, notice this, equal volumes of gases at the same temperature and pressure, so we're not changing those variables, they contain the same stuff. So more specifically, the same number of moles of gas. Now remember, if we're talking moles, then that also means we can talk about molecules, of how actually, if we could visualize how many little molecules are in there. So if we had a balloon, and in Mrs. Gunter's room there was a balloon that had 10 liters, and in Mrs. Cabani's room there was another balloon that had 10 liters. Mrs. Gunter's is in nitrogen, Mrs. Cabani's has helium, and in my room we have 10 liters and I have oxygen. If they all had the same volume, we would know that they all contained the same moles. Now they would have different masses because each molar mass is different, but we're not talking about that. We're just talking about the number of molecules or moles. Okay, to make it look like your formula chart, let's not really worry about this. On your formula chart, this is what it looks like. It's the V1 over N1 equals V2 over N2. So since pressure and temperature are the same, we can just ignore them in the combined gas law. So this problem's actually, most of them you can usually do the math in your head. I mean, it's still cross multiply doing the algebra, but this is algebra that's a little bit easier. So look at the problem. If a 5-liter sample of oxygen and it contains this many molecules, so remember moles is really the same as molecules. To get to mole from a molecule, you're going to times it by that number you love, 6.02 times 10 to the 23rd. So how many ammonia molecules would there be? We're talking about different gases, but it doesn't matter. That's what's the cool thing about Avogadro's. It doesn't matter which gas you had. Any gas at the same temperature and pressure is going to contain the same amount. So you would just set it up. So I know my volume 1 then is 5 liters. So we can also use moles like molecules then. You don't have to change it into moles, because to change it into moles, you're just going to do the same thing for both. So then you can call molecules or moles is 2 times 10 to the 23rd molecules. Okay, well, if I have 5 liters of, let's say, so this really isn't B1, this is actually oxygen. I want to know, well, I have 5 liters of ammonia. How many molecules are going to be in that one? Well, Avogadro has told me if I have 5 liters, and I know in that 5 liters there's 2 times 10 to the 23rd, sorry, I lost my sig figs, 2 times 0 molecules, I'm abbreviating, and I have 5 liters, this is oxygen, this is ammonia, How many molecules are in there? Okay, well, hopefully you can look at the math and realize, even though this is very messy, I apologize, that if I have 5 liters of oxygen and 5 liters of ammonia, Avogadro said if I have 2 times 10 to the 23rd molecules of oxygen, I have to have 2 times 10 to the 23rd molecules of ammonia. They're the same. Okay, so look at this next one. So if I have 5 liters of oxygen, okay, same scenario. I still have my oxygen, and I know I have 5 liters. Okay, this time, same. I have 2 times 10 to the 23rd. This time, in my volume of ammonia, oh, I have 10 liters. So how many molecules are going to be in that sample? So set it up to look at your relationship. Well, for every 5 liter of oxygens, this is my known value, I have 2 times 10 to the 23rd. Remember, that's just a big number. Just a big number is all it means because molecules are really small. So I have 10 liters of NH3. How many molecules are in there? Well, hopefully you can see the relationship. Now we can do our cross multiplying, crisscross, butterfly, whatever you want to call it, and divide it. We can also, this is where I said we can kind of use our logic, because if you look, how did I go from 5 to 10? This is a direct relationship. Well, that's times 2. Well, then how is this going to still be equal? You know you're going to have to times that by 2. So some of this you can do the mental math. You don't like doing the mental math, then go ahead and put it in your calculator. Cross multiply, set up the algebra problem, and solve it for x. Either way, I'm going to get an answer that I'm going to have 2 times that amount, which is 4 times 10 to the 23rd molecules. Double the volume, double the amount of gas. Okay, so if I have 5 liters of oxygen, and this time I said I have 2 moles, and so I'm giving it to you as moles, but I want molecules. So what I would do is figure out how many moles that's going to be, and then you can go from moles to molecules. So same thing, if I have 5 liters of oxygen, in that 5 liters I know I have 2 moles. Well, I'm going to compare it to if I have a 10 liter of ammonia, and you can do any gases, as long as they're at the same temperature and pressure. How many molecules are in there? Okay, well, what I have to realize, I can't really go to molecules first. That's not going to work. We're going to have to go to moles first because these have to be the same unit. So, look at your relationship. How did I go from 5 to 10? Well, it doubled. So if this doubled, it's a direct relationship. This has to double. So that means I must have 2 times 2 is 4 moles. Okay, yay, I'm done. Oh, no, I'm not, because Mrs. Mahoney said we have to read our problem. So I go back and read my problem. It asks, oh, how many molecules? And a molecule is not the same as a mole. So that means I'm going to say, well, for every 1 mole of ammonia, I know I have 6.02 times 10 to the 23rd molecules. So you're actually going to take 4 times the 6.02 times 10 to the 23rd. So what is your 4 times 6.02? That's going to be 2.4, because I know it's 24 times 10 to the 24th, but significant figures or scientific notation, we'll put it back. So that's how many molecules of ammonia exist. So if it's talking about moles and volume, and typically the way, kind of a heads up, they're going to talk about 2 different gases. That's like huge to know, is this what I'm doing? Look for 2 different gases. Okay. So now we're going to look at a special condition. It's looking at this STP again. We're going to realize that actually this step, when you see the STP, I know that I'm going to know a specific temperature or pressure. Well, what it also can be is a shortcut, because looking at this, there's a condition, and so it's kind of taken into account Avogadro's principle. What they have found out, that at that standard temperature and pressure, they started measuring a bunch of different gases, and they found out when all gases were at the same condition, SDP conditions, the 1 mole of gas always contained the same volume, and that volume is 22.4. So guess what? This is a shortcut. This number is on your formula chart. So where I say it's a shortcut, now let's kind of look at this. You can write this down, just kind of look at it. How many moles of oxygen gas are contained in 135 liters of oxygen STP? Okay, I'll be honest, at first this looks like a PV equals nRT because I don't know moles. I have a volume and it's not a 1, so I don't know why I just said 1. Okay, STP. Oh, I know what I can do. I can find that temperature. So my temperature is 273 Kelvin because I know temperatures always have to be in Kelvin. And pressure's at atmosphere. Oh, I just did these. I could find my R, 0.0831, sorry, 206. My AP and this are getting confused. 831. Nope, sorry, that's my KPR. That's our energy R. 0.0821. Sorry, had a moment that I got my numbers confused between the classes. I could do it using PV equals nRT and solve for moles. Okay, that's perfectly 100% acceptable. But we have a shortcut. Now, if you recognize the shortcut at STP, you can only do this shortcut at STP. I can do it using dimensional analysis. Now, here's the thing. Some of you don't like dimensional analysis. Use PV equals nRT. That's perfectly fine. But look at the shortcut. 135 liters. So, if I have liters right here, that's telling me liters is going to have to go on the bottom. So I know for every mole of oxygen, and I don't care what gas it is, it's going to be 22.4 liters. So this way I just know I'm going to take my 135 liters and divide it by 22.4, that I know is going to be 6.03 moles of oxygen. So this is why it's a shortcut. I could do this in one step using dimensional analysis versus having to list my variables, PV equals nRT. So recognizing STP can be a really, really good thing. Okay, so let's try a little bit more. 9. How many grams of nitrogen? Oh, well, remember from STP, there's no formula. Look at your formula chart. None of our gas formulas have grams in it, but they do have moles. And if I know moles, I can find grams. So I could do PV equals nRT, but no, I recognize my shortcut. So what do I know? 35 liters. Okay, it's nitrogen and 2 diatomics are going to get you in this unit. Well, I need to get to moles because I know to get to grams I have to get to moles. So for every 22.4 liters, I know I'll have 1 mole of nitrogen. Okay, last time I ended it here because it asked for moles. But now it asks for grams. So what do I know? Well, 1 mole of nitrogen. Molar mass, it's N2, 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 so the molar mass is 28 grams. So you're going to take 35 liters divided by 22.4 times your 28, so you would have 44 grams of nitrogen. Okay, I'm going to actually leave 10 to you. What about, let's look at 11. So you guys do this one. Let's look at 11. So this time I have grams and I want volume. And again, add STP. I could absolutely use PV equals nRT. If I use PV equals nRT, I'm going to change grams to moles. I'm going to look for volume. But I like shortcuts. So if I have 35, that says 34 grams of ammonia, I recognize I have grams. Well, I can only use STP if I have moles. I don't have moles yet, so I'm going to have to go to moles. So I know for every mole of ammonia, its molar mass is 17.03 grams. So that's how I can get to moles. But it wants volume. Volume, remember volume is liters. That's what I'm asking for. So for every mole of ammonia I have, it's going to be 22.4 liters. So we're really just working these backwards. So, I can do this. Future AP kids, we can do this one in our head. So look at what I know. 34 divided by 17, well, you have about 2 moles of ammonia. So if I have 2 moles of ammonia, 2 times 22.4 is 44.8 liters of ammonia. Okay, so if you kind of look, I know in my class I've said this the rest of the year is just like how many ways can we find the mole. So look what we know now. So I know mole, I can go from a mole to a gram. How do I do that? Molar mass. Well, if I had a mole, I could go moles to either atoms, remember if it's an element, or molecules if it's a compound. How did I do that? 6.02 times 10 to the 23rd. Now we can go from moles to liters of a gas. Again, this only works with the gas. And we can either use PV equals nRT, or I can use 22.4 liters. And most of the time when you're doing dimensional analysis, this is what you're using, is that 22.4. But the mole in chemistry is the center. That's what's important. Okay, so on the next time on our class, we're just going to work on figuring out these problems. When do I use which formula? Here's the thing, we've learned all the formulas now. Now we just need to figure out look for the clues. So that's what we're going to do before we take the quiz. We will see you in class.